When was the last time you built something from Lego? A single block is pretty simple, but if you have many blocks, you can start to build some pretty complex stuff. But when you look at the car or the robot that you've made, you can still see how every block fits into the whole. The real world is not like this. Although everything is made of the most fundamental blocks, atoms, the materials around us have vastly complex properties. That's because they're made of just so many atoms, all with a range of temperatures, thus a distribution of energies, all jumbled up and constantly interacting. All that we can observe is the collective effect of all those atoms, and information of interactions between single particles is lost. This is a problem, since in order to design better drugs to treat you, or better materials for your phone, we need to understand what's occurring at the microscopic level. So how can we do this? One idea is to build an artificial system, which we perfectly control. By studying how this model system behaves, we learn something about how real systems behave and build a picture of material interactions from the ground up. In my lab, we're starting from the simplest system, just two atoms side by side. Realizing this system, though, comes with a couple of challenges. Number one, I need to cool my atoms down to a millionth of a degree above absolute zero. By doing this, I'll be able to precisely control the quantum state. And number two, I need to isolate just a few atoms from the trillions around us to work with. The first problem is the trickiest. There is a way to make atoms ultra cold, but it only works for a few types of atom. That's why I choose the group 1 elements rubidium and cesium, whose particular energy level structure lets me cool them down using lasers. By applying lasers of just the right frequency, I can continuously remove energy from my atoms until I'm left with a cold, dense cloud of each. And now I can focus another laser beam down to a millionth of a meter, forming an optical tweezer. This tweezer, made of light, lets me reach into each cloud and pluck out two atoms, one rubidium and one cesium. And now I can start studying their interactions. For example, if I overlap my tweezers, I can study the collisional dynamics between the two. But why stop there? I could apply a magnetic field to my atoms and bind them to build a rubidium-cesium molecule. And if I started with several tweezers, I could build several of these molecules. I could then look at the interactions of an atom and a molecule, of a molecule and a molecule, three molecules, and so on. This platform, where we build increasingly complex systems from basic blocks, will be a powerful tool for understanding the interactions which underpin our world. Thank you.